Alright guys, so in this video we're going to be discussing rate laws. So reaction rate is actually dependent on two important variables. First of all, it's dependent on the concentration of the reactants that you have in your chemical equation, and it's also dependent on the temperature of the reaction. However, when we're discussing rate laws, the most important variable in this case is going to be concentration. So to give an example of how we can write a rate law, we can give the simplest form of a reaction in which one reactant is forming products. So here we have reactant A. And in order to write the rate law for this equation, we would say that rate is going to be equal to K, which is our rate constant of the reaction. It's a constant value for a specific reaction, times the concentration of our reactant A, raised to N, which is the order of the reaction with respect to reactant A. And so ultimately the order of the reaction with respect to that reactant tells us how does the rate of the reaction change as a function of concentration. So typically when we look at reactions, we'll see that the order, the N value, with respect to a certain reactant is an integer. And so we often see the order of 0, first, or second. And we can see that changing this value of N actually changes how we would write the rate law. So for example, for 0 order, rate is just going to be equal to the rate constant, because technically we would be saying our concentration of A raised to the 0 power, well, anything raised to the 0 power is just 1. So ultimately, rate is going to be equal to that rate constant. For first order, we can see that rate is equal to our rate constant times the concentration of A. And for our second order, we can see that rate is equal to our rate constant times our concentration of A raised to the second power. And as we change this overall reaction order, that actually leads to a change in the units of our rate constant K. So for example, for a first order reaction, we have rate is equal to the rate constant times the concentration of A. And we know that rate is a measurement of speed of the reaction, essentially. So molarity per second is the unit of the rate of a reaction. And that's going to be equal to our rate constant, which we need to figure out what these units are going to be, times the concentration of reactant A, which is in molarity. And so if we try to solve for the units of K, we will divide molarity over, and ultimately we can see that molarity is going to cancel in the numerator and in the denominator. And so ultimately our rate constant K is equal to 1 over seconds. And so that's ultimately how we get this unit of the rate constant for a first order reaction. Now the trend that we can see here is that as we go from 0 to first to second order, we are dividing by units of molarity. So ultimately we can say, okay, molarity per second divided by molarity, just like we just saw, is going to be 1 over seconds. 1 over seconds divided by molarity is going to be 1 over molarity times second. And the reason that this is occurring is because we're increasing the exponent of concentration as we increase the overall reaction order. And so ultimately, as the order with respect to a specific reactant changes, we're changing the relationship between rate and the concentration of that reactant. So for example, for our 0 order reaction, we can see that this plot, which plots concentration of our reactant versus the rate of the reaction, shows that regardless of concentration change, the rate remains the same. And so ultimately for a 0 order reaction, the rate of the reaction is independent of reactant concentration. Now if we look at a first order reaction, we can see that rate is equal to the rate constant times the concentration of that reactant, and we can see a direct linear relationship occurring. So ultimately the reaction rate is directly related to reactant concentration. And finally, if we take a look at a second order reaction where rate is equal to K times the concentration of a reactant raised to the second, we can see an exponential increase in rate as concentration increases. And so for a second order reaction, the rate is proportional to the square of the concentration of the reactant. And so if we continue this trend, we can see that a third order reaction with respect to reactant A, the reaction rate would be related to the cube of the reactant. Now remember in this video that we're just considering one reactant. In the next video we're going to discuss how to determine the order of a reaction and even consider situations where there are multiple reactants.